Okay. All right. So welcome back. The next talk is from Konstantin Wernli, who is at the University of Southern Denmark. We'll talk about on the Chern-Simons partition function in the Battalion-Witkowski formalism. This is what I've written in my notes, but here it says Chern-Simons theory and BV formalism. Very good. Please.
All right. So yeah, many thanks to the organizers. So first of all, for organizing such a meeting. I think we're all desperate for meetings, and also for the opportunity to speak. So since it's a junior conference, like 2/3 of my talk is going to be introductory. So I hope nobody gets really bored, but yeah, I think it should be all right. And so I'm going to talk about, the Chern-Simons theory in the BV formalism, and I hope I can talk to you about some recent ideas that I had together with Pavel Mnjov on the definition of the perturbative BV Chern-Simons function. And I think I'll explain more about the problem once we get there. But I want to start more or less at the beginning. So I'll talk a bit first about the way I see quantum field theory and functional integrals. And then I'll talk about two different approaches to path integrals. So path integrals and functional integrals are the same. This is a typo. And then lastly, I'll talk about the path integral in Chern-Simons theory and BV formalism. So lots of physics today is formulated using field theory, so especially particle physics. And the way I formulate field theory mathematically is as follows. So I'll take a manifold which models the space-time. And to that manifold, I'll associate a space of fields and an action functional on the space of fields. That should be local. So it should depend only, so it should be the integral of a Lagrangian which depends on the fields and its derivatives at any given space-time point. And classically, the physics is described by the solutions to the Euler-Lagrange equations, so by the principle of least action, right? So any field configuration phi that satisfies the equation that's here, a variation of action functional is 0, so that field configuration will describe the classical physics of the system. So for instance, to describe electromagnetism, I would take m equals to R4, right? So just usual Lorentzian spacetime, or even Minkowski spacetime. And then the space of fields is a space of electromagnetic potentials, which is a space of 1-forms on R4. And the Lagrangian, which is in the lower left corner. I don't know if you can see the mouse moving. So the mouse is moving over the Lagrangian of electromagnetism, which you probably all know. And classical field configurations would be plane waves.
We can see the mouse.
Perfect. Thank you, Friedrich. So, okay, one slide on classical field theory, next slide on quantum field theory. So usually the classical description for many phenomena fails when we do experiments at very small scales. And quantization is a process of, trying to reconcile the classical physics with our quantum observations, right? So we're making observations at very small scales. They're not governed by our classical physics. So we're looking for another theory coming from these classical physics describing the quantum phenomena. That's quantization. And there are many, many different approaches, and people have been thinking about it for more than 100 years, I guess. And quantum field theory can be described as the problem of finding some quantization process of classical field theory. And one method to do that is through path integrals. So what we're interested in, let's say in some, some simplification of quantum field theory, right, are vacuum expectation values of observables, and observables are just, some sort of functional on the space of fields, right? For example, the charge in electrodynamics would be an observable. And in quantum physics, instead of, these observables having a fixed value, we only can make a statement about the expectation value of those observables. And the crazy idea that, I mean, I say here it's due to Feynman, but apparently Dirac thought about it too. And some German physicist in the mid-20s already, but I forgot his name, like everybody, because nobody talks about him. So it's actually what we're observing when we observe quantum phenomena is that we're observing a superposition of all the possible field configurations. So it's not just one field configuration that contributes to what we see, like in the classical case, but really we are seeing the superposition of all the field configurations. So we know how to take an average in mathematics, right? So we take an integral. So we take this weighted average where we integrate over all the field configurations, the value of the observable weighted by this exponential term here. And those integrals over all field configurations are what I call path integrals. And the normalizing factor here is called the partition function. And okay, I see there's a typo here. This hypothetical measure d phi should be not in the exponent. So the partition function is just the integral of this exponential weight here. And so I'm going to say more about mathematics of those integrals in the next section. But the name path integral comes from quantum mechanics, where so the fields are paths from A to B, and so Feynman's idea really was that a particle is not taking a single path from A to B, but somehow it's taking all the paths at the same time, and we're seeing really a superposition. So there's this nice cartoon that I like on path integrals. So and it's about the path integral of your life, right? Probably many of you have seen it before. So there are sort of the more common life paths and more uncommon life paths. And as you might have experienced, your own life path is sort of a superposition of many different life paths that you might have chosen. And then maybe a second cartoon. So there's, if you don't understand these things, then you shouldn't be scared, because Feynman himself apparently said in a lecture, so this is from a really nice graphic novel on Feynman. So he said, so this business of understanding is serious, and I want to tell you something. The students don't understand it either, and that's because the professor doesn't understand it, and I don't understand it. Okay, so he had this idea, but he was saying that basically no one can really, understand the conceptual implications of observing a superposition of all realities rather than a single reality. Okay, so enough comics and philosophy. So mathematicians have really been on the hunt for the definition of the path integral. I mean, basically because the point is that it works, right? But it's not, there have been not really a general successful mathematical definition of it. So, and in fact, there hasn't been any really satisfying framework for quantum field theory that can explain all the details in reality. So, for instance, at least in my understanding, there's not a mathematically rigorous understanding of the phenomenon of confinement. So the confinement is what makes the proton stable, and what makes the proton stable is the fact that there exists matter in the universe is because of the stability of the proton, right? So I mean, we're still not mathematically understanding this very basic fact. And of course, you all know that one of the millennium problems is actually making mathematical sense of Young-Mills theory. One of the ways to do this would be through the path integral. Not the only way, but one of the ways would be to have a better understanding of the path integral. So that's why, you know, I like to do research on the sketches, because I think it's important that we understand more about these integrals, even though a lot has been said about them, but I think there's still a lot to say. So today I'll talk about this object here, the partition function, which, as I said, hinted at a couple of times now. So this, I'm putting colon equal, but this is not actually a mathematical definition, for the reason that, you know, usually there isn't a sensible measure on this space of fields, right? So, I mean, of course, you can put stupid measures there, but you would like to have a nice measure that's maybe translation invariant and certain things. So there is some work by Glim and Jaffe, and it's in 1D and 1 dimension and 2 dimension. You can do some things, but in general, this is really, really hard. So there needs to be an alternative approach. Not usually we think about integrals in a measure theoretic way, but this approach seems to not work for these functional integrals. So I'm going to briefly look at two ways that I could define this path integral, and I will call it, you know, a physicist and a mathematician's approach, but obviously I'm generalizing. I mean, it's long since been a giant overlap here. So physicists have been thinking about these path integrals in terms of perturbative quantization and Feynman graphs for a long while. So let me say, try to explain in a couple of slides what that's all about. So, so in perturbative quantization, we're taking a constant in our theory, which is very small. So that there are some constants in physics which are very small. And then instead of looking at this constant as a constant, we're actually let it become a parameter in the theory and let it go to zero, at least formally. And since the constant is so small, we're saying that, okay, from the asymptotic behavior, as this constant goes to zero, we can still extract some information about the actual physics. And for us, we'll do this with the Planck constant. So with physics, physicists usually do it with the coupling constant, actually, but this is it's more or less the equivalent. And so when you do this, so when you look at asymptotics of a oscillating integral, right, of this general form, you'll obtain a formal power series like that, describing the asymptotics. And this power series doesn't converge, but that's okay, because it describes the asymptotics of a function as that parameter goes to zero, and those power series don't always converge. And if you've never seen this formula, I'm just telling you that, you know, there is something called principle of stationary phase that tells you how to compute the asymptotics of those integrals. And the idea is really that this integral, as the constant becomes smaller and smaller, it's more and more dominated by contributions from the critical points of the action function. And that makes sense, right? Because h bar is somehow a parameter that measures, well, somehow h bar being non-zero means that we have sort of quantum phenomena in our theory. So if we let h bar go to zero, we are approaching the classical case. And classically, we know that the physics is described by the critical points. So this is just saying that as h bar goes to zero, we are focusing on something that's concentrated very closely to the critical points. And there will be some constants for each critical point, and then, you know, a formal power series associated to each critical point with certain coefficients ak of c. So how to compute those k coefficients? So they are the ones coming from Feynman integrals, Feynman graphs. All right, and so in the finite dimensional case, this is a theorem. So whenever both sides are defined, they're actually equal, or I mean, the right-hand side is the asymptotic approximation of the left-hand side. But since we are dealing with cases where we don't have a definition of the left-hand side, so we're taking the right-hand side, and we'll take that as a definition. So first we have to, generalize this to the field theory context, and then that will be our definition. Okay. So, so now a brief primer on Feynman graphs. So it's actually easier to understand Feynman graphs from the physics. So we're taking the standpoint that our field theory is describing some particles, and the particle has some physical information, like its position in space-time, maybe a color index, and maybe more. And there's sort of a basic ingredient in the theory, which is the probability that the particle changes its state from I to J. So that means changes, space-time position, color, momentum, you name it. And that probability is given by the inverse of the Hessian, at that critical point. So this is, so maybe let's take that as a sort of, I mean, this is a statement that sort of requires its own explanation, but I'm not going to get into that today. And also we might have a problem that the Hessian could be not invertible. So we'll talk about that in the next section. That's where the BV formalism comes in. And so now any number of particles which more than 3, so they can interact with each other, and we depict this as a vertex. So there's just particles, and the particles can interact with each other. So, and that will give us a vertex. Again, there will be certain probability which can be computed from the action functional. So just essentially by taking derivatives of the action function at the critical point. And now, so the coefficients AK, they're coming from the weights of certain graphs. So the graphs have ingredients, well, lines and vertices. And to compute the weight of a graph, we'll just multiply all the probabilities associated to the vertices and to the edges, and sum over all the labels, and possibly the labels are continuous, so then we'll integrate them. So let's look at an example, right? So coefficient AK is given by summing over all graphs with k loops, and there is you divide by number of orthomorphisms of the graph. Okay. So for instance, here are two graphs, gamma 1 and gamma 2. So here you would label, so you would have certain particles interacting with each other. And then the weight of this graph would be, so you sum over those probabilities. So you multiply all the probabilities. So P associated to the left vertex, P associated to the right vertex, and the transition probabilities. And then you would sum over all the possible labels. And to compute the coefficient A2, the two-loop contribution, so it's called two-loop contribution because there's two loops. So you would take the weight of the first graph and the weight of the second graph, and you would divide the weight by the number of graph orthomorphisms. So graph orthomorphisms are just ways to permute the edges essentially such that the graph looks the same. So in the first graph, and edges and vertices. So in the first graph, you can permute the 3 edges and the graph will not change. So that gives you 3 factorial. And you can also exchange the 2 vertices and the graph will not change. So that gives you another factor 2. So overall, you will get a factor of 12. So 1 over 12. Okay, so that was a super brief introduction to perturbative quantization and Feynman graphs. So any questions so far? If not, I'll just go on. So we've already heard a bit about TQFTs. So mathematicians were not very happy with perturbative quantization for various reasons. So when mathematicians are not happy, they tend to start from, from zero again. So they'll just come up with their own axioms. And there were plenty of axioms for QFT, like Osterwalder, Schrader, and others. And but for topological theories, there was a nice set of axioms put forward by Attia and Siegel, so around 1988. So probably since this is a junior conference, I mean, many of us were just born around this point, or not even born yet, but I mean, here we are. So here are the two main characters, Attia and Siegel, and yeah, I think you know who this person here is. He'll play a role later. So let me just briefly tell you what this does. So because it's actually it's very elegant. That's what it's nice. So a TQFT associates to a D-1 dimensional manifold sigma, a vector space with a pairing. So essentially it should be a Hilbert space. And to a D-dimensional manifold, it associates a vector that lives in the vector space associated to the boundary of that manifold. And this should be in such a way that, okay, to the empty D-1 dimensional manifold, you associate phi. And whenever you glue two manifolds together, you have this cutting and gluing axiom. So when you have two manifolds that you're gluing along a common boundary, you get two vectors in the associated vector space, and there is a pairing in this vector space, so you can pair these vectors together. And that's the number you would associate to the glued manifold. In particular, so this means that if you're to a manifold without boundary, to a d-dimensional manifold without boundary, you're associating a number because a number is a vector in C, right? So yeah, so this is a graphical illustration, right? So C of a sphere is you take C of the left half sphere, C of the right half sphere, you pair them together, they live in C of the circle, which is a vector space, and you'll get a number in C. Okay, so some remarks on this definition. So it's mathematically very elegant, and it has led to many new insights, actually in physics and in mathematics. So there's been a tremendous amount of research on this topic, far too much to say a lot more about this. But one problem is that, when we have such an assignment C, so these assignments, but they're actually functors usually. So when we have such a functor, it's not clear. So we remember that we're trying to find, like more information about the path integral. So it's not clear how these assignments are related to the path integral, right? But on the other hand, so in the perturbative case, I mean, at least for me, it's very clear. So you have an integral which is, well, it's not defined, but you're sort of like, if it was defined, then its asymptotics would be this. Okay, so it's actually a pretty straightforward thought. Whereas for these functors, I don't think it's as straightforward to make the comparison. And in today's main example, Chern-Simons theory, which has already been introduced before, that's the case. So there is is it on this slide? No. So then we've heard in the talk before about Reshetikhin-derived field theory. So it's supposed to be the field theory that gives you essentially the path integral for Chern-Simons theory. But how do you know it's really the path integral for Chern-Simons theory? So So there is some roundabout way, right? So it's a topological quantum field theory. So it associates something to two-dimensional surfaces, and that something is a quantization of the moduli space of flat connections of that surface, which, as Neschler explained, can be seen as a canonical quantization of Chern-Simons. But there's still no sort of direct relation to the path integral there. So maybe in the last 20 minutes, yeah, I'll try to explain in the case of Chern-Simons theory how you would try to make that connection. Okay, so so first I say a little bit about Chern-Simons theory, although I mean Neschler has said a lot about it already. So I take a three-dimensional manifold M, so I didn't write it, but M is supposed to be three-dimensional manifold, and I take so a connection on a trivial SU2 bundle and a connection, or actually trivialized SU2 bundle. So such a connection is defined by a global, one form with values in the Lie algebra of SU2. And you could put other gauge groups here. I'm just putting SU2 for concreteness, really. And then the action functional is the one you saw already. And I didn't put this normalization factor, but you could put k over 4 pi here. And as Neschler said, okay, everybody in this community probably has heard of this paper, which is really quite an awesome paper. So that explains how quantum field theory in the form of Chern-Simons theory is, related to the Jones polynomial. And I mean, its results are really quite elegant. So there's like basic observables in Chern-Simons theory. Their expectation value is sort of more or less the Jones polynomial. So that's nice. But this paper wasn't written at a sort of maybe mathematical standard of rigor, so we're still doing research and mathematical research on this. And I think Neschler said this also. So since this paper, the Chern-Simons theory has been the Drosophila melanogaster. So that's this fly that all the biologists study, because it's like it has this very simple genetics, so it's easy to say things about it. So Chern-Simons theory is sort of the main toy model for mathematical physics, because I mean there's some interesting physics. Physicists have thought a lot about it. It's related to 3D gravity. It's related to conformal field theory. It's related to knot theory. It's related to quantization of moduli spaces. And, so there's really many different ways you can approach Chern-Simons theory. And that's why it has been studied so much. So, yeah, so the Reshetikhin-Turaev theory, so they defined the TQFT like according to the definition I gave before. And that TQFT CK, so it depends on the parameter K, it coincides, almost with Witten's computations for Chern-Simons theory. So for experts, there's some slight subtlety about framing. So Witten uses a framing to define his partition function of Chern-Simons theory. Reshetikhin and Turaev don't need a framing. There's a paper by Attia sort of giving a explanation about this that I don't know how well it has been really understood, frankly. So there's still a slight subtlety, but I mean they're very similar. So the open problem that many people are interested in is whether the asymptotics of these so the asymptotics of this theory, or the corresponding invariance, as k goes to infinity. So k is something like 1 over h bar. so whether that coincides with the perturbative quantization of Chern-Simons theory. And that is really a question. So I try to explain why people care about this question, because it seems oddly specific, but the point is really that we want to have more insight on the path integral. And I think solving this problem would really be sort of a strong, very strong argument that Reshetikhin-Turev TQFT sort of is the correct value to assign to the Chern-Simons path integral. So maybe another argument, I mean, there are already some arguments, but I think this would be a very strong one. But there's a problem here. So I didn't write many formulas, but one formula that I wrote involved the sum over critical points. And so how does that even work in Chern-Simons theory? So there's another open problem. So what actually is what should we understand by perturbative quantization of Chern-Simons theory? And I'll try to explain some, partial answer that's also still work in progress. And by work in progress, I have to say there isn't really a draft yet. So it's ideas that exist mainly on paper and email conversations. So what are the critical points? So remember, we want to sum over the critical points, right? But so the critical points of the Chern-Simons action function are the flat connections, right? So there's a lot of flat connections. So there's usually, in particular, the flat connections are not isolated in the space of fields. So if I have a flat connection, I can act on it with a group element. I'll get another flat connection. And that means that whenever I have a flat connection, I sort of have an entire orbit of flat connections passing through this flat connection. And that means that I will have directions in which my action functional, so in which the Hessian of the action function is degenerate, right? Because I have somehow if I go into the direction of where there is a sort of, well, an orbit, my action function will not change. And that vector will be in the kernel of the Hessian. And that means it's not invertible. So that means the Hessian is degenerate and it's not invertible. And the basic ingredient in the theory is the inverse of the Hessian. So that's a big problem. And whenever we want to, perturbatively quantize gauge theories, we actually need a little more technology than what I introduced before. So that's where Bataillon-Wilkowiecki formalism comes in. So as I said, the gauge theories have non-invertible Hessians at the critical points because there is this gauge symmetry, which preserves critical points. We sends critical points into more critical points. And we should sort of try to restrict to a certain subspace of the space of fields on which the critical points are not degenerate. So if you imagine that my gauge symmetries are acting like this transversely, I should find some slice of the space of fields such that when I restrict the action functional there, then the critical points become isolated. And now it is another crash course on BV formalism. Obviously, there's a lot more that you could say about this. So I assume that my space of fields is a vector space, right? So in Chern-Simons theory, it's the case. It's a space of one forms. And I'll embed that space of fields in a super vector space, which I call curly FM. And that supervector space has an odd symplectic form, and it has a reference half density mu. So that's a technical detail. And I want to extend my action functional straight Sm to something called curly Sm. in the structure sheaf of this supervector space that satisfies the classical master equation. So I have a symplectic form. That symplectic form gives me a Poisson bracket, and that Poisson bracket is odd. In particular, it makes sense to look for, functionals satisfying this equation. And now what you do is you're choosing a Lagrangian inside this odd symplectic space such that the extended action functional restricted to this Lagrangian has non-degenerate critical points. So these non-degenerate critical points are important because they are, if we don't have them, we can't write down the perturbative quantization because we can't write down the propagator, the inverse of the Hessian, and we can't have Feynman graphs. And so once we have all this, if we have the non-degenerate critical points, okay, then you have to trust me that there's a way you can make sense of the perturbative expansion for odd symplectic spaces. So just one word, so I have a half density here. So a half density, when I restrict it to a Lagrangian, it becomes a density and I can integrate densities. Okay, so from that point of view, this makes sense. That's going to be important later. So why is this good? So there was a choice that I made. So there was this choice of the Lagrangian, right? So that's a problem because I'm trying to compute something that shouldn't depend on a choice. I mean, originally this Lagrangian, this like an artificial piece of data. So it turns out that there is this canonical operator on 1/2 densities on finite dimensional supermanifolds. And if I assume that delta, so this is called the BV operator. So if the BV operator applied to S times my reference half density is 0, then the classical master equation, so S bracket S equals to 0, implies that the BV operator applied to this exponential here vanishes. Okay, so that's the quantum master equation. And then if I have this quantum master equation, there is a theorem that, okay, the integral actually doesn't depend on the Lagrangian. So very nice. And the integral is in fact equal to the original integral I was trying to compute. So here I should be careful with mu and d phi and everything. Okay, so and in infinite dimensions, that's really all heuristics, and what we have to do once we computed the perturbative partition function, we have to show by hand it's not dependent. It doesn't depend on this Lagrangian. And then there's another little something I have to talk about, which is the BV push forward. So in some cases, you won't be able to find this Lagrangian directly inside all fields, and you would have to restrict to an odd symplectic subspace. And then you could push forward the BV theory from the original space of fields to a symplectic complement of this symplectic subspace where you have the Lagrangian. So this inclusion is the wrong way. It should go, the Lagrangian should be in here. And in that case, the BV push forward, and this should read mu, I'm sorry. So it just means I'm integrating over alpha. There will be another half density, which now sort of is a half density on this new BV space. And the BV theorem extends to this case, and it tells us that the partition function is closed with respect to the BV operator on the smaller space. Okay, so now I have 5 minutes left, so let's maybe get going with Chern-Simons theory in BV formalism. So there's a really straightforward BV extension of Chern-Simons, which you can check by hand, or you can use a KLC construction that I think will be talked more about later in the conference. And now what I'll do, I'll work around a reference flat connection. And so I fix some connection A0, and I consider the linearized theory on the tangent space to A0. And the tangent space still looks the same because it's still a vector space. But what changes is that I'm replacing the de Rham differential now with the de Rham differential twisted by the flat connection A0. And so now the gauge fixing can be done using a Hodge decomposition. So I'll choose a Riemannian metric. Then I have the co-differential, so the formal adjoint of this twisted de Rham differential. So this is not the BV operator. This is the Hodge de Rham Laplacian associated to A0 and this metric. And I have a Hodge decomposition into harmonic forms, exact forms, and co-exact forms. And now this is again an odd symplectic space. This is an odd symplectic space. And in here, so in Y, I have a Lagrangian, which is just given by the co-exact form. So you can check that the symplectic form actually vanishes on here. And restricted to this Lagrangian, my action functional at A0 has a unique critical point. So that's what I like. And so now I can compute, again in quotes, this perturbative partition function in the following way. So it now depends on the thread connection, on a field in, so on an element of A, on V, and on the Riemannian metric. And now I can just, so this integral that's written here, this is an integral I can evaluate using Feynman graphs because it has non-degenerate critical points on this Lagrangian. Okay, so here's the definition. The Chern-Simons partition function at A0 is, well, Chern-Simons exponential of Chern-Simons action at A0. Raysinger torsion, square root of the Raysinger torsion, e to the I pi over 4 times eta invariant of A0 and G, and then the perturbative series given by Feynman graphs. And yeah, if you want to know more about any of these, you can maybe ask me later in the discussion session. And the graphs look like this. So there is a field labeled, there is a leaf labeled A, and then there are vertices, trivalent vertices. Okay. So these are some examples. And okay, to compute the weight, you pick an orthonormal basis of SU2. And then again, you label all the vertices and half edges. Okay. And then to an edge, you'll associate the integral kernel of this map here. So you can check that this is actually the inverse of dA0 when restricted to the gauge fixing Lagrangian, so two co-exact forms. And for a leaf, you multiply with the field A. For the vertex, you multiply with the structure constants, and then you sum over all the labels, you integrate over n. Okay, so here's an example. I won't say more about that because I'm running out of time. So here's a remark. So if you take all the tree diagrams and sort of extract them from the perturbative series, then you can actually see that, so there is a problem because here we have a 1 over h bar in the exponential. So that means we have infinitely many negative powers of h bar, right? So that's not very nice. But we can see that they just sort of live in this prefactor. And the rest of the perturbative partition function is contained in a formal power series in h bar. with values in formal 1/2 densities. You can show that the cohomology class of C is almost independent of G, so that relates to this framing story I was talking about before. But now we should sum, over all the flat connections. So yeah, how do we do that? So maybe if I have 2 more minutes, then I'll sort of try to explain how to do that.
Yes, please.
I think I was, aware of the fact I would be short on time on this point. Yeah, so how does the perturbative partition function on A0? So today I'll talk about a bit about how the propagator depends on A0 and how that influences the partition function. So there were other ingredients like randomized torsion, eta invariant. So I'm not talking about them today. So here's a small lemma. So so how the propagator. So the propagator is the integral kernel of this map. And if I vary my closed form, sorry, if I vary my flat connection along a path, tangent vector alpha, right? So if alpha is a tangent vector to a path of flat connections, it's going to be dA closed. Then this is how the chain contraction changes. This is how K changes. And this means that the integral kernel changes like that. So I'll take, so eta is the integral kernel and it changes like this. So this term here corresponds to K circ at alpha circ K. And this term here corresponds to this commutator. Well, this in terms of Feynman diagrams, this means that if I take an edge and hit it with a time derivative, then somehow that edge will grow an extra leaf, okay? And the first result is that when alpha is exact, then your path of flat connections actually comes from a gauge orbit. And then you can sort of use the standard BV techniques to show that you're changing your partition function by a BV exact term. Okay, so then in this case, if you have alpha is dA0 of something, then if you're just sort of adding in these D exact terms, then there are some methods to show that you're in BV cohomology, you're not doing anything. So the BV cohomology class of this partition function, it will descend to the moduli of flat connections. And now there's a particular type of flat connections that are called irreducible. So this is irreducible flat connections are when first cohomology of that flat connection vanishes. And in that case, the partition function only depends on the parts of the cohomology in degree 1. So in principle, it depends on all degrees. But if you don't have cohomology in degree 0, it only depends on the cohomology in degree 1. And also in that case, there is a neighborhood of this point in the moduli space of flat connections, which is modeled on this cohomology. So, and there's actually a map induced by the Riemannian metric from from the tangent space at A0 to the moduli space of flat connections. And then the claim, so this is the result that we're trying to write down, is that if I have a component of the moduli of flat connections which consists of irreducible flat connections, then the partition function evaluated on A is the pullback via this map phi g when I set A to 0. And so what does it mean? So this object here, And so I'm running out of time, so I'll close now. So this object here, that's actually a formal power series with values in real half densities, not for on the moduli space of flat connections. So in particular, if I have such a component which consists of irreducible connections, I can integrate this guy here over that component. And then that would be the contribution that I assign to that component sort of the moduli space of flat connections. And now if I have a dense subset consisting of such sets, then yeah, so my guess would be that the definition of the perturbative partition function is just summing over those components the integral of this density here. So it's a 1/2 density, but if you restrict it to this thing, it's a density actually. So it's a density, you can integrate it. And that is our guess for the perturbative partition function that you know, should be compared with asymptotics of Reshet-Tikin-Tarayev. And it, okay, I mean, it has the correct looks. And yeah, I'll stop here because I'm way over time. So thanks.
Thank you very much. It was a great talk. Thanks.
Yeah, sorry for going over time.
No problem. It's very interesting. So are there any short questions? Okay, so we have a question from Julian or Julian. I'm not sure. Sorry if I'm pronouncing it wrong.
I'm Julian.
Yeah.
Hello.
Okay, just a short question. Can you incorporate Wilson loop in your pictures, like associate a co-cycle to frame links?
Yeah, I mean, in principle, yes. So we haven't thought about Wilson loop yet in this framework, but it should be more or less straightforward.
So you can compare to Konstantin invariants.
Yeah, so
Homology class, I mean, the H0 of the
Konstantin invariant is not invariant, right? I think Konstantin invariant would be if you take the manifold to be R3. And
that's the easiest case.
Oh, Julian, I see you here. Here you are. So I have a face. So yes. Yeah, I mean, you can try to do that. So there is a paper by Fröhlich and King, also from '89, where they are, I mean, they actually consider also not invariance or invariance of links in R3, and they show directly the relationship to Chern-Simons. So, I mean, the idea is in R3 you have a special gauge fixing that renders the theory abelian, so you'll have no more vertices.
And can you hope?
I don't think there is a mathematical proof of this. So.
Can you hope to have surgery formula to relate cohomology of cohomology class you create?
Sorry, I didn't understand acoustically.
Can you hope to have surgery formula related different three manifold? It's something that quite common in, for example, LMO invariants, which are perturbative invariant of three manifold created from surgery. Can you imagine having some kind of, once you have nodes inside the game, you can.
Yes, so I'm actually, I mean, I hope. I mean, in my PhD, I was working on extending these theories to manifolds with boundary. So you would think about what happens when you actually cut and glue the perturbative expansion. Yeah, I can't say we have, arrived at a surgery formula yet.
Okay.
But I mean, that would be ideal, I guess.
Thank you.
Thank you. Yeah.
Okay. All right. So then we have a question from Friedrich, please.
Hi. Yeah.
Hello.
Thank you for the talk. I have some foundational question, from the beginning when you were comparing the perturbative Chern-Simons and the Reshetikov Turayev thing, and you said that we need to take the limit of the level going to infinity. So is this? It's probably something that I should know, but this Reshetikov Turayev thing, does it have a k parameter in it, or it probably doesn't, right?
Sorry, my speaker is doing weird things. Yeah, it does have a k parameter, so I'm actually not the expert here to ask. But
but you would still expect that the coincidence, that it coincides with Chern-Simons only in the limit, or is it expected also for a finite k?
So I mean, the point is we don't know how to compute the path integral for finite k, right? So I mean, the kind of logic I'm trying to do is, so I want to have strong argument that Reshetikov Turayev at level k corresponds to the path integral of Chern-Simons at level k. So what I'm doing, but I sort of have this definition for the asymptotic limit of the path integral, which is sort of a kind of natural definition because it just extends to the infinite dimension, a finite dimensional concept. So I want to show that that coincides with the asymptotics of the original guy.
I see.
And,
okay. But in the ideal world, in the infinite future, people would probably see that also for you can have a finite k.
Yeah, I mean, yeah, it really depends on who you ask, right? I mean, many people will tell you, okay, this is the quantum Chern-Simons at level k, that's the Reshetikov Turayev.
Okay, I see.
But there are some things there which are not fully understood, especially maybe the path integral question.
Okay. Thanks.
Thank you very much. We have another question from Marcus, please. So.
Thank you. In the last slide, you have given an idea how to calculate the functor associated with Chern-Simons theory as a topological field theory using the path integral. So my question was, there's of course also this idea to describe Chern-Simons theory as an extended topological field theory. So that you would also give awareness of this functor for not only for D manifolds and D-1 manifolds, but also for D-2 and lower manifolds. Are there also possibilities to describe this perturbatively, or is there any hope to do that?
There's hope. So yeah, here I didn't say anything about the functorial. So this is just for closed manifolds. You can define the partition function at some fixed connection also for manifolds with boundary. In certain cases, that was sort of a part of my PhD. But I mean, there's different approaches. I mean, in BV formalism, you can only do it for certain Lie algebras right now, but I'm sure we can do it for all Lie algebras soon. Here it's really about summing the different perturbative expansions. So you have one for every flat connection, right? And the question is how to put them together so that you get a single formal power series. And eventually maybe you resum that formal power series, you would have a single number, right? So that's the goal. And yeah, you can do it. I mean, in principle, there is nothing from stopping you about perturbative quantization on manifolds with corners. I think Nima also likes it, right? I think many people here like it. So there's certainly, I mean, I didn't talk about BV-BFV. I'm not sure is there a talk about BV-BFV in the conference?
I think it's not actually.
But there's I mean, a group of, so we are working on this idea of extending BV formalism to boundaries, and you can extend it to corners and higher codimension.
Maybe there is the talk of maybe Giovanni talks about it. But
he doesn't talk about quantization. So quantization for corners is still something we have to understand correctly. Yeah, we would like to do it, but yeah.
Okay.
We'll get around to it in the future.
Okay, good. I have a couple of questions, but maybe we can talk. A bit more. Good. So there are no other questions. Great. So thank you again for the great talk. So let me pause the video.